Good evening, our students, and welcome to this hour's class. Today, we'll be looking at another very important topic in statistics, which we refer to as moments. Moments. The big question here is, what is moments? What do we regard to be moments? The simple thing we can say about moment is that it is used to describe the distribution of a random variable. That which helps us to describe the distribution of a random variable in statistics is what we refer to as moments. This moment, of course, is going to be discussed under two major categories. And these two categories are what we call the theoretical moments and what we call the sample moments. So we have number one, we are looking at what we call theoretical moments. Theoretical moments. Theoretical moments. And then what we call sample moments. That is number two, sample moments. Sample moments. So beginning from the first one here, talking about the theoretical moments, we are now going to give what we call the mathematical expression of theoretical moments. And of course, theoretical moment is denoted by E of x raised to power what k, where this E stands for expected value or expectation, and this x stands for a random variable. And this k, of course, stands for that particular moment we are interested in. And here we are talking about the kth theoretical moment. However, this theoretical moment is going to be discussed equally under two categories. One, theoretical moments about the origin, or what we call theoretical moments about zero, and then theoretical moments about the mean of the random variable. The denotation I have here is, of course, what we call the theoretical moment about zero, or theoretical moment about origin. And it is expressed this way: sum over the range of x of k raised to power x raised to power k, probability of x being equals to x. It can only be expressed this way if and only if there is an additional information that this random variable x is a discrete random variable. That is when we use this word sum. However, if we have an information that this random variable x is not discrete, instead it is a continuous random variable, then this kth moment about the origin will be expressed as this. This becomes integral over the range of x raised to power what k of f of what x, the what of the x. So this is an expression of kth moment about zero. This is an expression of kth moment about zero. The only difference between this and this is that while in this first one, x is a discrete random variable, in this second one, x is a continuous random variable. Now, I use the word here, kth. Kth is not specific. K can be 1, k can be 2, k can be 3, down the line. Therefore, this k has a range, and the range begins from 0. So we say where that small letter k is equals 1, 2, 3, down the line. So what are we going to say when k becomes 1? What are we going to say when k becomes what? 2? We see the illustration here on the board. When k becomes 1, what we are going to have there becomes what? A of x raised to power 1. In place of this k, what I'm having here becomes what? 1. In the expression I have here, it becomes that this equals sum over the range of x. Here is my x raised to power k. Now k has become 1. So it's going to be x raised to power 1. P of capital X is equal to small x. That becomes the expression when that happens. The next question becomes, in mathematics, when something is raised to power 1, what does it imply? Anything raised to power 1 in mathematics becomes itself. Therefore, this is the same thing as writing A of x is given as sum over the range of x of x. P of capital X is equal to small x. This is what we call the first moment or first theoretical moment about the origin, which is always called the expected value of that random variable x. What happens when k becomes what? 2? When k becomes 2, what we are going to have becomes what? A of x raised to power 2 is given as sum over the range of x raised to power 2 p of capital X is equal to small x. The same thing applies when it becomes what? 3. We have a of x raised to power 3 is given as sum over the range of x raised to power 3 p of capital X is equal to small x. Okay? So this is what we call the first moment about the origin, second moment about the origin, third moment about the what? Origin down the line. So you can talk about the fourth, you can talk about the fifth down the what? The line. They follow the same pattern. We did this illustration believing that x is a discrete random variable. If x ceases from being discrete and becomes continuous, the only changes you are going to have here are in place of this word sum, you are going to make use of what? Integral. So it becomes integral of x raised to power whatever moment you are interested in, f of x dx. That is what we call theoretical moment about the origin or about what? Zero. How do we explain a theoretical moment about the mean of the random variable? Permit me to clean this one. Remember, we are still discussing the theoretical moments, but we are making this discussion under two categories. When we are talking about what? Theoretical moment about origin, and when we are talking about what? Theoretical moment about what they mean. We are just done giving illustration about theoretical moments about origin. So let us now discuss the theoretical moment about the mean. So I clean this place. Okay. Of course, you know that conventionally, the population mean of any random variable is always denoted with a letter this, mu. We call it mu. While the sample mean is denoted with the letter what? X what bar. So when we talk about the theoretical mean or theoretical moment about the mean, our interest is about this population mean mu. So in that case, what I'm going to have becomes what? E expected value of x minus what? Mu, all raised to power k. This is how we denote the theoretical moment about the mean. This is mean here. If this mean becomes 0, this equation here reduces to what we had earlier. And we should be talking about the theoretical moment about 0. The moment this mu becomes what? 0. But when this mu takes up any other value other than 0, we should now be talking about the theoretical moment about what? The mean. How are we going to express this thing? Still the same way. When this x is discrete, we are going to say that it becomes what? Sum over the range of x. Then we open a bracket, x minus mu, all raised to power k. Then we have p of capital X is equal to small x. This is what we are going to have. Like what we met earlier, when we ask ourselves, what happens to this equation when x becomes 1? when k becomes 1, what happens when k becomes 2 down the line? If it becomes 1, this is what we are going to have. We have sum over the range of x. We have x minus mu. This is x minus mu, all raised to power 1. Then we have p of x is equal to small x. And like I earlier had said, when anything is raised to power 1, it becomes itself. And then this thing can be written as sum over the range of x. You open the bracket, x minus what? Mu. You have p of capital X is equal to small x. Implying that when k becomes 2, you know where you are going to fix in 2. When k becomes 3, you know where you are going to fix 3. And down the what? The line. These are actually what we call the theoretical moments about the mean. So do permit me, and of course remember that when this x becomes a continuous random variable, this sum which you have here now becomes what? Integral. It is now going to become what? Integral. So you permit me to clean here. Let us take real life example and be able to show the much which we have given on the board. But as a quick recap, remember that this is the first moment about the origin, 0. Look at how it is expressed when x is a discrete random variable. This is second moment about the origin, 0. Third moment about the origin, 0, down the line. If you come here, this is the expression for the kth moment of a random variable x about the mean mu. When this k becomes 1, this is what we are going to have. When k becomes 2, of course, you know what you are going to have down the what? The line. I want to believe that you have had much on the theoretical moments about the origin and the theoretical moments about the mean. Let us now discuss briefly the sample moment before we go ahead taking questions. Thank you very much for your audience. Okay, the two words here are theoretical, believed, and then sample, taken away from the population which we are seeing concrete. So we are now discussing the sample moments. We are on to sample moments. Sample moments. Okay? Most of the time, the sample moment is denoted with M subscript what? K. Where this M stands for the first letter in the word moment. And this K, of course, stands for that particular moment that we're interested in. Here we are talking about what the get what moment. So the question is, how do we express this? And do remember equally that in this sample moment, we will be talking about the sample moments about the origin, 0. And then the sample moment about the mean of the random variable, say x or y or anything which you have defined it to be. So first one, we are discussing the sample moment about the origin, 0. And I say if I write m subscript k, it is now going to be expressed as sum over the range of what? Of x. Okay? Of what? X raised to power what? K all over n. This is what we call the kth moment, kth sample moment about 0 or about origin. So the question becomes, of course, you know that my k takes value 1, 2, 3 down the line. So what happens when k becomes what? 1. When k becomes 1, what I'm going to have here is what? M subscript 1 is given as sum over the range of x. Here is my x. This k becomes what? 1. all over what? N. But still remember that we say that once anything is raised to power what? 1, returns itself. Therefore, this equation becomes what? Sum over the range of what? X. Of x all over what? N. You bear me witness that sum of x all over n is what we call the mean of random variable or mean of observations. Therefore, the first sample moment about the origin or about the mean, about 0 is the mean of the random variable x. I repeat, we gave a formula for the kth moment, sample moment, about the origin, about the 0. Look at the expression. K takes value from 1 down to positive infinity. We are now saying, what if k becomes what? 1? K became 1 and we substitute 1 here. After manipulating on this formula now, we arrived at this, which you know is the formula for what? For the mean. And we are saying, what conclusion can we arrive from what we have seen on the board? The conclusion is that the first sample moment about the origin or about the 0 is the same thing as the mean of that random variable x. Pin that one down very well. What happens now when k becomes what? 2? As usual, what we are now going to have becomes what? M subscript 2 is given as sum over the range of x raised to power what? 2 all over what? N. So that is exactly what we're now going to have this time around. So anytime you see this kind of equation in statistics and they ask you, what does it stand for? It stands for the second sample moment about the origin or about 0. So when k becomes 3, of course, you know what you are going to do. When k becomes what? 4, you know what you are going to do down the line. We want to show sample moment about mean. Sample moment about what? Mean. So it permits me to clean this side of the board. Do remember that when we talked about the population mean, we said that we represent population mean with what? Mu. We represent it with what? With mu. Mu this way. But when we talk about what we call the sample mean, we represent it with what we call x bar. Permit me to remove what came on my screen. We represent it with what? X bar. So if I want to talk about the sample moment about mean, I am going to write this. M subscript k, which is the kth sample moment about the mean, is going to be given as what? Sum over the range of x, you open a bracket, of x minus x bar all raised to power k all over what? N. This is what we call the kth sample mean about mean x bar. The other time it was about mean mu, because we are talking about theoretical. Now we are talking about sample, we are saying about the mean x bar. What happens when k becomes 1? What happens when k becomes 2? Let us look and see. When k becomes 1, what we are going to have becomes what? M subscript 1 is given as sum over the range of x minus what? X bar. It's needless writing 1 here because you know anything raised to power 1 returns itself. So I will now have all over n. This is what I have. When k becomes 2, I'm going to have m subscript 2 is given as sum over the range of x minus x bar all raised to power 2 all over n. And you bear me witness that the formula which I have here is the formula for the variance of a random sample or variance of observations. So what conclusion can we reach from here? The conclusion we can reach is that the second sample moment about the mean is the same thing as the variance of that random sample x. I repeat, when we say let k become 2, we substitute 2 in place of this k. And after manipulating this gate formula, we arrived at this formula. Coincidentally, this formula becomes the formula for the variance, which we know. We now say, what conclusion can we make? The conclusion is simple. That the second sample moment about the mean of that random variable is the same thing as the variance of that random variable x. That is another thing I would want you to pin down in this our class. So what we are going to do quickly is to take a sample or take real life data and be able to show one or two things which we have discussed here. So permit me to clean the board while we take real life example. Okay, what we are going to do is this. Let us call this one example 1. Let me call it example 1. Example 1. In this example 1, I have a table that goes this way. This is the table. The random variable I'm interested in is what? Is x. This is my p of capital X being small x. Okay? So I have these values here. Here is my 1. Here is my 2. Here is my, or let me start with 0 if I like. Here is my 1. Here is my 2. And here is my 3. Then let the probability of this one be 0.2. This is 0.4. This is 0.2 again. So we now have that this and then this is 0.2. Because the sum of all the probabilities must give us 1 before we can say that that distribution is a true probability distribution. And if you say 0.2 plus 0.4, 0.6, plus 0.2, 0.8, plus 0.2, that is 1.0. So the first question here is for us to find the first theoretical moment about 0. So the question says find A. That A says E of x, which is what we showed earlier to be the first theoretical moment about the origin. Then the second question says find E of x raised to power 2. Another hint, information I want to give you is a hint. They are moments about the origin. Moments about origin. It is about the origin. The origin. So we quickly go to that formula, which we showed earlier, which I will now recall for you. We had earlier that the kth theoretical moment about 0 is given as E of x raised to power k is expressed as sum over the range of x raised to power k p of capital X is equals to small x. This is the expression of it. But this time around, I'm interested in the first moment. So where k is 1. If k becomes 1, here I will have E of x raised to power 1 is sum of the range of x raised to power 1, p of capital X is equal to small x. In this class already we have told ourselves that this raised to power 1 is the same thing. So we have E of x is given as sum over the range of x, p of capital X is equal to small x. This is the formula we are going to use, which is exactly the same thing they asked us here. So we now come here. So this is equals. Sum here means addition. X here, look at the row for x here. P of capital X equals to small x, look at each row here. So what we are going to do is pick a value of x, use it to multiply the value of what of its probability, plus. We now go that way. So this equals. The first value of x here is 0, so I have 0 multiplied by its probability is 0.2. So I have 0.2. Because of this sum, I will say plus. The next value is 1. Its probability is 0.4. So I have 1 multiplied by 0.4 plus. The next value is 2. So I have 2 multiplied by. Its probability is 0.2. So I have 0.2 plus. The last one is 3. And I have 3 multiplied by 0.2. When 0 multiplies anything, it goes off. So this quantity is removed from here entirely. When 1 multiplies anything, the answer remains that thing. 1 times 1 is 1, 1 times 2 is 2. So 1 multiplying anything doesn't really have effect on that thing. So 1 multiplied by 0.4 here will give me 0.4 plus. 2 multiplied by 0.2 will give me 0.4 equally plus. 3 multiplied by 0.2 will give me 0.6. So I have what? 0.6. So it is now for us to add. 0.4 plus 0.6 equally, it has already become 1. 1 plus this 0.4 will give me 1.4. So this thing becomes 1.4. So the first theoretical moment about 0 in this problem I have on the board is given as a 1.4. And I equally want to make you to learn this thing from me today, that the first theoretical moment about what? 0 is the same thing as the expected value of that random variable, e of x. They are the same thing. So let us now go over. The one we solve here is for question what? I. So it's for question I. So let us now solve for II. So you permit me now to clean this side and then solve the II there. II now is e of x raised to power 2. E of x raised to power 2. So that II, like I said, is for us to obtain e of x raised to power 2. We are not going to waste time here. We are just going to put raised to power 2 here because it means the same thing. So this is the same thing as sum over the range of x raised to power 2, d of capital X is equal to small x. What is implied here is when you take any value of x now, you must first of all have to square it before you use it to multiply the probability. The first value here is 0, so we have 0 raised to power 2 multiplied by 0.2 plus. The second value is 1 raised to power 2 multiplied by 0.4. The other one is 2 raised to power 2 multiplied by 0.2 plus. This one is 3 raised to power 2 multiplied by 0.2. Okay? So what we are going to do here is 0 raised to power 2 is 0. 0 multiply anything is gone. 1 raised to power 1 raised to power 2 is 1. Because 1 raised to power 2 means 1 times 1, and 1 times 1 is 1. Multiplying by 0.4 will equally give me 0.4. So plus. 2 raised to power 2 will give you what? 4. Multiplying by 0.2. And then 3 raised to power 2 will give me what? 9. Multiplied by 0.2. This is what we are going to have here. So because I do not have calculator present at the same time, the moment you evaluate this thing now, that becomes apparently the second theoretical moment about the origin, 0. So that's how to go about this. We want to believe so far that when we ask you to find the third moment, ask you to find the fourth theoretical moment, the fifth one, and the rest of them, it is very simple. It's a question of now, this place now become changing here. If they say here is third, you put 3. If they say it is fourth, you put 4 down the line. Thank you very much for your audience so far. Let us equally draw another sample and discuss about the sample moments. This one we talked about is on the theoretical moment. Let us talk something on the sample moments. So permit me to quickly clean here. Sample moments. This time around, let me have observations this way. Just very small observation. This observation I have is this. I have a tray. I have three. I have four. I have five. I have six. Seven. Let me have this kind of observation. Then I have something like nine, and I have let me take values that we can easily get their mean. We have one, we have two, three, four, five. Where 1 plus 2 give us 3, to this will give me what? 6, to this will give me 10, to this will give me 15, and we have 1, 2, 3, 4, 5. We have 5 observations. So the question here is, using these data points I have on the board, obtain the first sample moment about the origin, second sample moment about the origin, and equally obtain second sample moment about the mean. So that is what we are going to look at here. So see what we are going to do. The question they ask us to do is, using this observation, this example 2, is example 2. Using this question, they say obtain number A is, I have M of what? M1, or let me put MK when K equals 1. They mean the same thing. And then ask you M2, MK when K is equal to what? 2. This 2 here is talking about the origin. About the origin. The origin. Then let me quickly say that when I'm talking about number B, this number B is asking us to obtain M of what? K when K equals 2. When K equals 2, then I have M of K equally when K is now equals to what? 3. This time around, it is about the mean of the random variable. So here is about the mean. About the mean. So there is a big difference between these moments here and these moments here because of the location of their origins. The origin here is 0. The origin here is the mean. So about the origin 0 here. So let me come over here and say solution. Solution. We first of all call up the formula for the sample moment, kth sample moment about the origin 0, which is the first segment of what of the questions. Do you remember earlier that we had mentioned that M subscript K is given as sum over the range of x raised to power K all over N. But this time around, they ask us when K is equals to 1 and when K is equals to 2. So I'll first of all consider when K is what? Is 1. So when I consider when K is 1, it is going to be M subscript 1 is given as sum over the range of x raised to power 1 all over N. You and I know that this x raised to power 1 is the same thing as what? As x. So what I'm going to do simply becomes, and this sum means I should sum all this value of x and divide by n, where this n is talking about the sample size. And the number of data points I have here is 1, 2, 3, 4, 5. They are 5 in number. So I have something 1, the next observation 2, plus 3, plus 4, plus 5. All over what? 5. This is equals. 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 5 is what? 15. So I have 15 all over 5. And from what I know, 15 divided by 5 is going to give me 3. Which means I'm able to find out that the first moment about the origin, 0, of these data points I have on the board is what? Is 3. And remember clearly that we earlier had said that the first moment about what? 0 is the same thing as the mean of that random variable. Because look at the formula for mean. So the same thing, the answer is what? Is 3. For us to find when k is going to be what? 2, we are going to go direct. In place of this one here, I'm going to write 2. So what I have becomes what? M subscript what? 2. Here it is now going to be sum over the range of x raised to power what? 2 all over what? N. So the only difference between here and here is the power of x here is what? Is 1, and the power of x here has become what? 2. So you are first of all meant to square the observations before you sum them to divide with the number of what? The observations. You take 1, you square it, you sum over to the last one. Therefore, what I have there becomes this equals. The first observation here is 1, so I have 1 squared plus. Here is what? 2 squared plus. Here is what? 3 squared plus. Here is what? 4 squared plus. The last one is what? 5 squared. All over, you still have what? 5. Permit me to call it up here and then conclude the solving. Okay, so you now come over here, this equals 1 squared is 1, so you have 1 plus. 2 squared is 4, you have 4 plus. 3 squared is 9, you have 9. 4 squared is 16, you have 16. And then 5 squared is 25, you have 25. All over what? 5. So you now say 1 plus this 9 here is, of course, is what? Is 10. Plus this 4 here is what? Is 14. Plus this 16 here will give us 40. And then to this 25 will give us 65. You can cross check that with your calculator. I'm doing this in off heart. So I have 65 all over 5. So 65 all over 5 is actually the second moment about the origin 0. Second sample moment about the origin 0. So what we're going to do is, I haven't shown you how to go about getting moments about the origin. Then we now come down to the second segment now and explain to you how to arrive at the moments now when your interest is about the origin. So you permit me to clean here as a fast recap, moments about the origin when k is equals to 2, square the observations before you divide it. When we treated out of the first moment, first means the power is 1. And anything raised to power 1 is the same thing. That was why we simply summed without squaring. If they ask you to find a third here, what you are going to do is to cook the observations by saying 1 raised to power 3 plus 2 raised to power 3 plus 3 raised to power 3 down the line before you divide by 4. Goes down to when it is 4, when it is 5, and then the rest of them. So let us look at about the origin or about mean. Okay, so let us quickly come over here when k becomes this. We first of all remind ourselves the kth sample moment about the mean. It is given as m subscript k is given as, we have sum over the range of x, open a bracket, of x minus x bar, all raised to power k, all over what? N. It was what we gave earlier as our kth sample moment about this mean x bar. Okay? Now, when our interest is when k is equals to 2, they ask us to find it when k is equals to 2. Anywhere you see k, replace with what? 2. And this formula quickly becomes m substitute 2 is given as sum over the range of x minus x bar raised to power 2 instead of k now all over what? N. Which I did say earlier that it is the same thing with the variance of the observations. So what is implied here is, first of all, obtain the mean of the observation. Subtract the mean of the observation from each of the observations. Once you subtract, you square, and then we go together. This equals. By a way of obtaining the mean x bar is given as sum over the range of x of what? X all over what? N. That's the formula for mean. So this is equals. Getting the sum of x means 1 plus 2, 3, plus 3, 6, plus 4, 10, plus 5, 15. So this is 15 all over what? 5, which is equal to 3. Which of course is an agreement with what we had earlier when we looked for the first moment about sample moment about the origin 0. That was why we said that the first sample moment about the origin 0 is the same thing as the mean of that observation. Remember, we had a 3 and we are still having that 3 here. So we want to use this now to find this. So we now say therefore that our m substitute what? 2 is given as. Look at the formula. So first of all, you have to subtract the mean from each of the observations. The first observation here is 1. So you open a bracket. You say 1 minus. X bar here is talking about the mean. The mean is 3. So you say 3. You close the bracket. All raised to power 2 plus. The essence of this plus is because of this sum which you have here. Because that's actually a point you are summing. Then you come to the next one. The next one becomes what? 2 minus 3. All raised to power 2 plus. This one becomes what? You have what? 3 minus 3. All raised to power what? 2 plus. The next one is 4. So you have what? 4 minus 3. All raised to power what? 2. And the last but not the least becomes plus. You have what? 5 minus 3. All raised to power 2. You know it is all over 5. Because the number of the data point is what? Is 5. Okay? So we now come here. When you come here, 1 minus 3 is minus 2 in mathematics. You have 1, but you are owing 3. So if you pay with your 1, you will be owing 2. So it's minus 2. So minus 2 squared means minus 2 times minus 2. And minus times minus is plus. So you quickly have that minus 2 raised to power 2 is what? Is 4. So what you have here becomes 4 plus. 2 minus 3 is what? Is minus 1. Minus 1 squared is just 1. Because we are talking about minus 1 times minus 1 plus. Here is 3 minus 3 is 0. 0 raised to power 2 is 0. So here is 0 plus. Here is 4. 4 minus 3 is what? Is 1. 1 raised to power 2 is what? Is still 1. You have 1 plus. Here is what? 5. 5 minus 3 is what? Is 2. 2 raised to power 2 will give you what? 4. All over what? Over 5. We come back here. 4 plus 1 will give me 5. Plus 0, 5, plus 1, 6, plus 4 will give me 10. So I have that this is equal to what? 10 all over what? 5, which gives me what? 2. So I'll be able to have that the second moment about the mean is what we have as a 2. While the first one about the moment, look at about the sample moment, about the origin, was just but 3. But this one is giving me 2. So when they ask you for that of what? 3, you quickly substitute the value of what? 3 in place of this place. So here becomes what? 3, here becomes 3, here becomes 3, here becomes 3, down the what? The line. So for now, I want to believe that we have done much looking at moment. First of all, we began by asking ourselves what a moment is, where we simply said that moment actually helps us to describe the distribution of a random variable, be it x or be it y. We now talked about looking at a moment under 2 major categories called the theoretical moments and what we call the sample moments. In the theoretical moment, we equally classified it into 2. Theoretical moment about the origin 0, and then theoretical moment about the mean of that random variable say X or say Y. We gave their expressions. We equally talked about the theoretical moment about the mean of that random variable. Before we now went down into the sample moment, in the sample moment, we equally talked about the sample moment about the origin, 0, and then the sample moment about the mean of that random variable x. There were things that we pinned down, and those things are, word of recap, that the first sample moment about the origin is the same thing as the mean of that random variable. And then the second sample moment about the mean of that random variable is the same thing as the variance of that random variable. One thing we are going to tell you in another class we are going to have, because the essence of calling up this question or this topic today to discuss is because we are planning to go and discuss what is called skewness and kurtosis. And we cannot discuss these two parameters without having to know about these moments. Because oftentimes when you go through the pages of textbooks, you hear them say that the third moment about the mean of the random variable is the same thing as skewness. And they will say that the fourth moment about the mean of that random variable is the same thing as the kurtosis. We are going to discuss it in details when we come to our next class, when we should be talking about measures of shape in statistics. Thank you very much. Remember to subscribe to our YouTube channel as well. Drop your comment in the comment sections if you have a challenge in any of what we have discussed today. Once we come across it, surely we will come across to assist you. Thank you and stay tuned for our next class.